on this computer. So from now on, we are recording, and
Professore, scusi, posso fare una domanda?
yes, please.
E per l'esame si potrà sostenere l'orale anche in italiano o per forza in inglese?
The oral exam can be, you can take it in Italian. Yes,
Okay.
no problem.
Thank you.
So let me share the screen. And we will continue with our description of the different types of satellites. But in order to make the story a little bit less boring, we will switch back and forth between the description and the examples. So to do that, we spoke about Earth observation satellites, and I would like to give you an example of an Earth observation satellite. And I took as an example, so let us move on. I took this example, which is the TOPEX Poseidon mission, which is a really fantastic mission. Let me just I would like okay, here show grid video. I want this on the side. I don't know why. It's over there and creates a lot of how can I put it on the side, the bar? Okay, I will iconize everything. All right. Perfect. So the TOPEX Poseidon mission is a very peculiar Earth observation mission devoted to the measurement of the sea level rise, and in general characterize seas, waves on seas, tides, etc. So what you see here is the spacecraft as it was, and we will describe it. But before going into the description of the spacecraft and try to understand also the requirements that a similar mission may have, let us look at the mission from a system point of view. So the goal is to measure the sea level, but the sea level with respect to what? Of course, with respect to the spacecraft. And what TOPEX Poseidon did was to send radar pulses, chirps, and compute essentially the travel time between the spacecraft, the sea surface, and back to the spacecraft. So the delay between the reflected signal received on board and the transmitted signal provided the altitude of the spacecraft with respect to the sea. So you can understand immediately the principle is very simple. It's the principle of a radar. But you can also understand immediately what the limitations are. The limitations are that even at microwave frequencies and JSON Topex Poseidon used S-band frequencies, wavelength of 13 centimeters or so, with an antenna sized on the order of the size of about 1 meter, the footprint on ground is pretty broad. So you have studied already space telecommunications, so you have an idea of what the half power beamwidth of an antenna is, right? And the half power is relatively large. So the areas covered, you can see it here. Let me grab the laser pointer for the time being. The footprint of the antenna is fairly large. So Topex Poseidon was measuring average properties of the sea and sea height over an area that we can also compute. We can make a very simple computation. 30 centimeter, let us say 10 centimeter and 1 meter diameter antenna makes for a half power beamwidth of 1/10 of a radian, okay? So about 5-6 degrees. Orbiting at 800 kilometers, you can see multiply this number 1/10 times 800 kilometers means that the footprint is several tenths of kilometers. Okay? So average properties over a large surface. Of course, there are ways to make the footprint smaller. Increase, and we will see during our course, one possibility is to increase the frequency of the radio waves, the waves that are sent, transmitted, used by the radar altimeter, or to make the antenna bigger, have a bigger antenna. It's important, of course, that the spacecraft is nadir pointed, so the optical axis of the antenna must be nadir pointed, although the requirement is not so stringent. Why not using a laser altimeter? A laser altimeter is a much more sophisticated instrument, but the problem is that it doesn't work very well over sea surface. It's excellent for ice because it provides a good reflection on ice, also on land, but not on sea. So this is the reason why sea level missions require radar altimeter rather than laser altimeter. But what kind of requirements on a general level such a mission may have? You see here a GPS antenna. Okay. And the reason why we need GPS antennas is because we want to transform a substantially dummy measurement, such as the distance between the antenna and the sea surface, which is a relatively, let me say, stupid measurement. It tells you the distance between two objects. Okay, between me, for example, and that wall. But we want to transform this measurement into a dynamical measurement on which, from which we can infer properties like the height of the sea. Height of the sea with respect to what? Because we need to define a reference frame. The reference frame is our geographical terrestrial Earth-fixed reference frame, which has its origin in the geocenter. Those of you who have made who took the space environment course last year know quite well about this. The geocenter is let us say, the center of mass of the Earth, including its atmospheric masses, all liquids, etc. It's an abstract point that can be extremely well determined by tracking the orbit of satellites. Because nobody has gone there and has set something the geocenter. Is an abstract point, but is the origin of our terrestrial coordinate system. And all the satellite orbits are defined with respect to a reference frame, which may be inertial or Earth-fixed. So a geographical frame which rotates together with the Earth. So we have to transform this distance measure in order to know what is the sea surface height. What we need? We need to know first the distance between the spacecraft and the geocenter, the origin of the coordinate system, or to a reference surface that we call the reference ellipsoid. Again, those of you who took space environment know what the reference ellipsoid is. But let us say the geocenter. Then we need to know, we need to measure, of course, this distance between the sea surface and the spacecraft. And by taking the difference between the distance of the spacecraft or the satellite with respect to the geocenter and the radar altimeter measurement, we can obtain the sea level with respect to the geocenter, which is what matters to us. So one important and fundamental requirement of such a mission is to know exactly and with the utmost accuracy the position of the satellite with respect to the geocenter. So we can make the best radar altimetric measurements, very precise, etc. But this precise measurements has little meaning if we don't associate to it a precise determination of the orbit of the satellite. All right? And this is why we are using Topex Poseidon is using a GPS antenna, because a GPS antenna, through GPS, we can position the satellite fairly well. It's not the only way, because other systems are used, the DORIS system, which is based on Doppler measurements, and on the latest generation, JSON, there are also laser retroreflectors, so that from ground we can shoot a laser beam to the satellite and get a return by means of this laser retroreflector, which is a corner cube. Is just the edge of a cube, and it can be demonstrated that the edge of the cube, independently of the direction of arrival of the laser beam is reflected back in the same direction. So this is another way to obtain a good determination of the orbit, and we will devote part of the course to see how we can determine the orbit of a spacecraft. But this is the first requirement. The second requirement, of course, we spoke about attitude. The measurement accuracy depends on the power that is available. So we need a large power to do a good measurement. So the radar must be a fairly powerful radar. And in addition to this, we need to correct for the path delay due to propagation into the atmosphere. The space between the satellite and the sea surface is not empty. There is a medium, the atmosphere, and the speed of light in the atmosphere is not the speed of light in vacuum. So when we do the computation on the round trip light time, we need to take into account that propagation occurs in a medium, not in vacuum. We have to take into account, in particular, the refractive index of the atmosphere. If I can, if we want to write some equations, let me grab the pen. The path delay, L, is equal to the integral over the ray path in the geometric optic limit of n, which is the refractive index, in dl. Okay, so if this is the path, and this element is dl, we need to integrate the refractive index, which is unity for vacuum, but is not unity for a medium like the atmosphere. And we can write this equation as equal to L0 or Lg, the geometric path delay plus a delta path delay, which is equal to the integral along the ray path of 1, the refractive index in vacuum, plus, we call it nr, the refractive index of the medium, in dl. So delta L is equal to the integral of NR in the L. This NR is small and has contributions from the dry troposphere, the atmosphere, but also from water vapor. Water vapor, the water molecules are polar molecules, so their refractive index is fairly high, and they can make up very easily to 20 centimeters of additional delay. And if you want to measure sea level changes that are of the order of a few millimeters per year, or 1 millimeter per year, you imagine that you need to calibrate the contribution coming from the so-called wet troposphere, which is the water vapor dissolved in the atmosphere, very well. And there are specific instruments called water vapor radiometers. And you see it here. Let me grab the laser pointer once again. You see here this antenna is the antenna of the microwave radiometer, which is an instrument that allows to calibrate with fairly high precision the path delay due to the water vapor content along the line of sight. So, going back to the structure of the spacecraft, we have here the altimeter antenna. It's this is the direction, the nadir direction. So the antenna points to the sea. We have nearby a laser retroreflector assembly. So the retroreflector, I told you why they are needed. We have an instrument module, which is all this box, which contains the electronics of the radar altimeter, plus the electronics of the microwave radiometer. And then we have a service module on this other side. This is a possible design of the spacecraft. It's not unique, but the system engineer has chosen to separate completely these two modules. It's something, a practice, which is quite common. Separate the instruments from what is providing services to the payload. Okay. And we have a radiator here. We have another small antenna for the Doris system, which is a positioning system French used by the French based on Doppler. We have the the GPS antenna up here, and the GPS antenna helps is used for orbit determination. And the power is provided by a solar array, which is put here. We have also a propulsion module because we need sometimes to do correction maneuvers. And this is hosted here. Finally, we have a high gain antenna. I don't remember the link in which band it was, but we have a high gain antenna to transmit the data from the radar altimeter and the instrument and the radiometer to ground, plus all the housekeeping data, all data that inform mission control about the health status of the spacecraft. This is one of the possible designs. But if you have to set requirements for a mission like this, First of all, very good orbit determination. Second, very high accuracy altimetric measurements. Okay? And you see here that the entire system, you have a laser ranging station which helps with orbit determination together with the GPS satellites and the DORIS beacon system. And you can see also that the sea level, the sea surface is not that flat. It's not spherical. Is an equipotential surface which depends on how masses are distributed inside the Earth. And the sea surface, in the absence of tides and wind, is called the geoid, and it constitutes the reference surface to provide altitudes on Earth. So all cartographic systems are based on the geoid. Our height is such and such above sea level. Okay, because sea level is a surface which is equipotential under the influence of the gravity field of the Earth and the centrifugal potential, the rotational potential. Okay, so is an equipotential surface. And everyone has access to it. Because we go to the sea and we know that the potential, gravitational plus rotational potential, at the sea level here or in Hawaii or in Patagonia is always the same for everyone. So it's a good reference surface for everyone. And you see that is undulated because depends on how masses are distributed on the seafloor and inside the Earth. So these are the two main requirements. Generation of power also is important. And you see here, power is provided, of course, by solar panels. There are some interesting results which came from these missions, in addition to the sea level rise. I won't go into this, but one interesting topic is the amount of sea level rise measured by TOPEX Poseidon and its follow-up mission, which is called JSON-1. And today we have another similar mission called JSON-2. And you can see it's from 1993, set in the zero. These are millimeters on the vertical scale. And sea level has increased if we trust these measurements. Today, the data here reached 2008. I should have a better, on the web, there are better measurements than this. And you can see, therefore, that in 20 years, essentially 3 centimeters. This is the amount of sea level rise on average detected by JSON-1. Okay? An example of an Earth observation mission, which is something very different from the one that you will hear about in the course of remote sensing with my colleagues from DIET. If you want to know more on this type of mission, there is a course on space geodesy that you can take for those of you who are interested. Okay. So let us go back. So we spoke about Earth observation satellites, telecommunication satellites. I won't say much because it's something that will be described fairly well in the telecommunication course. And a telecommunication satellite has to distribute signals from one point on the Earth's surface to the other. So Earth, space, Earth, but there are also conditions in which we have space, space, space. The so-called relay satellite, or Earth, space, space. Another situation where we have a relay satellite, a satellite whose task is to relay information, radio signal, for example, from one place to the other. And so far, all telecommunication satellites were based on radio microwave signals. So you see here also some considerations that I make. In telecommunication satellites, we can consider also TV satellites. Those of you who are using Sky are subscribing satellite networks. For example, the signal comes from space, one to many. But if you go in the United States, in most areas, in the big cities, etc., you won't see a single antenna dish because nobody uses reception from space of a TV signal. You can do it far more efficiently with optical fibers. And even today, in our homes, optical fibers are really a privileged way to convey information. I'm personally, in the past, transatlantic phone communications were obtained through geostationary satellite, and one can feel the delay, clearly the delay, by speaking from this side of the Atlantic to the other side of the Atlantic, for example. But the day in which the first optical cable, fiber optical cable, was deployed on the Atlantic seafloor, that single cable had a capacity which was twice the sum of all the 16 satellite channels available at that time, just to give you an idea. So for distribution of large amount of data, and now we are producing a huge amount of data, space is not the way. At least this is my personal opinion, shared by many. With a caveat that there are areas where it's economically not convenient to bring a fiber optic, to bring a cable, and for those areas, so for limited portion, for a small amount of the Earth population, it may be more convenient to get telecommunication in data, internet, quote unquote, through space rather than over cables. But in general, I don't see a big future for this. And now, you know, they are speaking, Elon Musk is speaking of thousands of satellites providing internet everywhere in all remote places of Earth, etc. Let us see how it goes. The first company went belly up very recently, and it's not a good start for this type of communication system. But there are people who believe in it. And for example, in the 90s, in the late 90s, there was the idea at the start of the development of the cellular networks, there was the idea of using space to provide a cellular network. And companies made huge investments because everybody believed in the possibility to use space to communicate with others. And there were two consortia, Globalstar and Iridium, who put in orbit a fairly large number of satellites, two constellations of satellites in LEO orbit. Iridium gave a global coverage for even the polar regions. And in principle, one can make a phone call from every point A to point B of the Earth's surface. But it was, both companies, both consortia went belly up. Even here in Rome, the satellite of the Globalstar constellation were built here in Rome. They were producing something like 40 satellites in 4 months. So a large number. But it wasn't a success story. Why? Well, I use satellite phones. I am a user. When I go in remote areas, when I do my hikes in the canyons of the American Southwest, alone or with my graduate students, we go every year to do these adventures. So we stay 1 week without meeting anybody. We rent one of these satellite phones for emergency. Because it may take several days before one can reach a road, okay? Well, in remote areas, it's certainly useful, but the satellite phone is 0.5 kilogram, is this high, and in order to work, you must be in view of the satellite. So if there are obstacles, if you are in the bottom of a canyon, you have to wait for the satellite to pass over the canyon, and you have, let us say, 1 minute, 60 seconds to send a text message or make a short communication. In open space, it works, but even trees, not to speak of buildings, you cannot make a phone call from this room through space on an Iridium phone. So these are the limitations and the reason why these constellations and these telecommunication systems failed in the past. They were kept, Iridium was kept alive by military funds because of possible military use. But I'm rather skeptical. It's difficult to fight against Earth-based systems. Also because the space technology, in spite of all the efforts that have been made, the space technology is born obsolete. Why? Because in order to develop a space system, it takes time. Much more time, about 2 or 3 times as much as developing a similar ground-based system. So it takes time. And by the time you design the system and you launch and make it operational, the ground technologies have advanced so much faster to make they are hard to beat. Okay? So this is my personal view. There are people who, for example, Elon Musk certainly thinks differently. The CEO of Thales Alenia Space thinks differently. Let us see who will be right. We have to wait a little bit. So I acknowledge the value of space telecommunication systems of this kind to reach remote areas, to let us say, to cut the digital divide, because there are areas, even in Italy, where high-speed internet is not available. So for that, it may be useful, but on a general scale, for most of the human population, I don't think this is the way to go. So telecommunication satellites, there are two big classes. One, completely obsolete and no longer used, geostationary, and the other, low Earth orbited satellites, constellations made up by many elements, possibly talking to each other, not talking only to ground, but talking to each other and establishing communication, inter-satellite communication. So a constellation of such type must have the possibility of having a link to ground and inter-satellite links with all the other nodes of the constellation, which is quite interesting, really very interesting. The next category of satellites I want to talk about, and we will see what is the payload and what the requirements are navigation satellites. Navigation satellites, let me see, what time is it? Oh no, it's time to stop. So we make a break here and we resume in 15 minutes. Okay, so we make the break now and resume in 15 minutes. I would like, sorry that I went long. I have to put my wristwatch here. So we will reconvene, let us say, at 11:20. Quanti di voi hanno fatto il corso di ambiente spaziale l'anno scorso? Sì, non tu, metà circa. Eccoci, siamo pronti a riprendere. Mi raccomando, distanziatevi il più possibile. So let us restart. And the next category of satellites we will describe are navigation satellites. Satellite navigation is a word by itself, and it would deserve a course by itself. Because the use of space for navigation is, I think, one of the most important and most interesting endeavors that have been undertaken in space. The original idea came from the military world, because positioning an object, of course, can be done in several ways, but rather inaccurately with terrestrial systems. If you want something global that works everywhere on the surface of the Earth, you have to rely on space. And the first system that was put in place by the US Navy was the transit system, a relatively simple system where satellites transmitted a radio signal of constant frequency, and the end user, which was a sophisticated user, not like us, was able to do a Doppler measurement, and through the Doppler measurement, after a few minutes of data collection and data processing, essentially the user could position itself. The user generally was a submarine, and the system was made for ships, especially for ships, and for ships in fixed positions and not moving. It worked a lot better if the object was fixed. But the transit system was the need for a better system than the transit one soon raised, and it was clear with the development of high accuracy, very stable atomic clocks in the 70s, a new system was conceived, the Navstar GPS system, what became the global positioning system. And the global positioning system is essentially a way to transfer coordinates from one point to the other on the Earth's surface beyond the horizon. So to a user which was beyond the horizon of another user. Today, there are several of this system. During the course, we will talk about GPS in detail. We will look also at relativistic effects on GPS, and I will introduce GPS when talking about relativistic effects. Today, there are several other systems. We have Galileo in Europe, which is a sort of imitation with some difference of the GPS. We have GLONASS, Beidou in China, also India now wants its own navigation system, and so on and so forth. So the principle of GPS is incredibly simple. It's the principle of triangulation, and we will describe it, but not now. And the concept, however, I can tell you what the concept is. The concept is that if you have a constellation of satellites, and actually GPS was really the first constellation, space constellation. If you have a constellation of satellites that transmits synchronously radio signals together with their position in a reference frame, in the terrestrial reference frame, for example, we will define it precisely. Then by triangulation, it's possible for a user to find its position. The concept is very simple. We will see how it works. We will not do it now. But we will describe the system. What is the payload? What are the requirements? What kind of orbits are used for this type of, let us go to the description of GPS satellites. What type of orbits? Well, the chosen orbits are orbits which have a period of 12 hours. So the position of the constellation repeats itself every 12 hours. And the altitude is about 20,000 kilometers, so we are in the so-called MEO orbits. In principle, a GPS satellite or a GNSS satellite, more generally, GNSS is an acronym for Global Navigation Satellite System. Navigation, one could say, put emphasis on position, because GPS is global positioning system. Navigation is something more. But GPS is also a navigation system. So all these GNSS systems are made up by a set of very simple elements. The payload, what is the payload? The payload are accurate, stable clocks. And in particular, every GPS satellite hosts 2 rubidium clocks and 2 cesium clocks for redundancy. And we will again describe these clocks later, especially the cesium clock. So this clock provides a stable time reference on board. And suppose that you are able to synchronize the payloads of all the constellation and create a so-called GPS time. in truth, is quite difficult. And what is provided is the difference between the time of each clock on board the satellite to the time of the constellation, which is defined elsewhere at the master control station, where even more stable clocks are available. So this, let me see if I have the pen, or no, I have the laser pointer. These satellites broadcast, let us say, I make it very simple. It's really not that way, but broadcast radio pulses through this set of antennas at frequencies L-band, 1.2, 1.5 gigahertz, and they broadcast these radio pulses synchronously. Let us assume that it's not that way, but let us assume that the distribution is synchronous. So the net outcome is that a user on the Earth is provided by a radio pulse and the position of each satellite, what are called the ephemerides of each satellite of the constellation that is in view at that moment. And let us, since I don't have the board, I have to share, stop sharing for a moment. I had a blank slide. And we see a little bit how it works, because otherwise, so. New slide. Okay. Let us share again. I should have prepared this earlier. And so let us go in presentation mode, take the pen. So the basic principle is very simple. We have an observer here on ground. We have 1, 2, and 3 satellites. And all this, let us assume for the time being, the satellite 1, 2, and 3 transmit simultaneously a radio pulse. Okay? Suppose for the moment that the observer O has a clock which is synchronized with the clock of the constellation, which is not the case. So, if the satellite 1 transmits its coordinate x1, y1, z1, and the same is true for satellite 2, x2, y2, z2, and here x3, y3, z3. Okay, and they transmit their position to the user here, which is has a position unknown x, y, z. Okay, we can write equations, which so I draw only one line, but there are 3 radio links. We can write equations of this kind, assuming propagation in vacuum, C square delta t square, where delta t is the delay between the transmission time of the radio pulse from satellite 1 and the reception time from the observer O. And of course, this is known quite well. Why? Simply because we assume for now that the observer O has a clock which is synchronized with the clock on the constellation. So we apply Pythagoras theorem. This is x minus x1 squared plus y minus y1 squared plus z minus z1 squared. So we can write this equation, okay? And for satellite 2, we can write a similar equation. Delta T2 square equal x minus x2 square, and so on and so forth. And the third equation for satellite 3, T3 square is equal to x minus x3 square plus blah, blah, blah. So we have three equations in three unknowns, the unknowns being x, y, and z, because delta T1, delta T2, and delta T3 are measured by the end user, by the observer O. And in principle, we can solve for the position of the user. However, while on board the satellites, we have a very stable clock and very accurate timekeeping instrumentation, this is not true for the end user. If I want to position myself, I cannot have a clock which is synchronized with GPS time. I would like to be synchronized to GPS time. So the problem is solved, and we will see how it's solved. Now I tell you only how it's done. By introducing a fourth satellite and a fourth link, and introducing a new unknown, which is which let us call it delta t, which is the difference between the time marked by the clock of the observer O and the GPS time, which is unknown. You can factor in this time difference in all these equations and have and solve therefore for four unknowns, having four equations available, the fourth equations coming from a fourth satellite, satellite 4. So by triangulation, essentially, by using Pythagoras theorem, assuming propagation in vacuum, and there are many ways to correct for ionospheric corrections, tropospheric correction, etc., and make the system very precise. We solve for the coordinates of the end user and the difference in time between the time marked by the clock of the observer O, the end user, and the GPS time. So very simple in principle, but its actuation is complicated. Far more complicated than you may think. So the first, the essential element of the payload is a set of clocks. And you use rubidium, which are far less stable, and cesium atomic clocks. Galileo, excuse me, uses hydrogen masers, which have an even better stability. So in principle, could provide better positioning, but this has yet to be seen. And so this is again the first requirement, having a payload made up by stable clock. The second requirement at system level of this constellation, what is in your opinion? We said it already. Synchronization of the clocks. So all the clocks of the constellation must be synchronized, must send radio pulses in a synchronous way. De facto, synchronization, perfect synchronization is not possible. What is provided in the navigation message is the offset of the time of each satellite with respect to the time of the constellation. But this is therefore a correction that you can make to bring the signal of that particular satellite in line with the time of the constellation. So the control station does not tweak, changes the position of, come si dice, lancette di un orologio. Qualcuno me lo ricordi? Ce l'ho sulla punta della lingua. Hands? Non mi torna.
Confermo che si dice hands.
Hands? Io avevo in mente qualcos'altro. Comunque, diciamo hands. Ok, thank you very much. So I don't change the hands of each clock because that would be complicated. It's done occasionally when the separation is too big. But generally what is provided is simply an offset. And then synchronization. So how do you know this offset? And synchronizing two clocks is much more tricky than it may look at the first time. And we will speak of synchronization later on in the course. I will give a special lecture on special relativity with a little bit of general relativity for what concerns GPS. And you will see that synchronizing clocks is not that easy. Okay? It's not, it's quite tricky. So synchronization, find a way to synchronize the clocks or to know the clock bias. And this is done together with orbit determination using Kalman filters. And we will talk about Kalman filters quite a bit in this course. So first, synchronizing clocks or knowing the clock offset. What is the other requirement if you look back to this horrible drawing that I made here? What is the next important system requirement that you have to put? I would say if you want to do a good job, you need to know very well what is the position of, what are the position of the satellites. So X1, X2, X3, the ephemerides of the satellites must be known extremely well. The orbit must be known well. Because if you make a mistake in the orbit and the satellite one, instead of being at its right position, it's farther away, let us say 50 meters away, you make an error in the estimation of the light time, and positioning degrades very rapidly. So good orbit determination is again an important requirement of this system. Orbit determination is done of the GPS satellites there is a group of people. There are a number of stations deployed on the Earth surface. There are 13 stations plus a master control station. They acquired data from the radio signal emitted by the GPS satellites, and in addition they use laser retroreflectors for doing orbit determination independently of the clock bias. They put everything into a big Kalman filter, and the outcome are the ephemerides of the satellites that are uploaded on board by the master control station and broadcasted to the users. So when your cellular phone positions yourself and gives you your coordinates, it has decoded the navigation message. And so each satellite that is in view at that time has transmitted also its position. A set of coefficients through which, with a simple law, interpolation, generally used is Keplerian, osculating elements of a Keplerian orbit, the position can be obtained at every time. Okay, so good orbit determination. However, these ephemerides, these coefficients that are distributed, become obsolete with time, because the orbit accuracy degrades with time. And so what the master control station does is to update continuously the ephemerides, and when the difference between the real position and the transmitted position exceeds a certain value, which is, say, 10 centimeters or so, it uploads a new set of ephemerides. So the ephemerides are continuously updated. So this is the second requirement. Good clock, synchronization of the system, and very good orbit determination. When we speak about navigation with GPS, navigation with GPS is a trivial thing. But because everybody can do navigation with GPS, I have okay, on my cellular phone, the right app, and I can find my position, I can decide where to go, how much time it will take with a given speed, and so on and so forth. But the clever part of the GPS system resides in this code and this dynamical, in the dynamical model that allows to compute clock biases and ephemerides. And it's a complex program. There are many now, not only military, also civilian programs. And some of them are available even for free. The Bernese, for example, Gypsy, developed by JPL, and so on. So that's the clever part of the system. And so very simple. You see here beyond the antennas that are used to transmit the signals, you have where is the S-band antenna? The S-band antenna is up here. This is a UHF antenna, and there are also retroreflectors for orbit determination, plus solar panels. Now, GPS used several types of satellites from the first block 1 satellite. They are divided in blocks. This is a block 2A on display in San Diego at a museum in San Diego. This is the last generation of GPS satellites. The concept is the same. Solar panels, array of antennas with a given antenna patterns, and the payload is inside. Okay? So relatively simple. The orbit is not geostationary. It's better to stay closer to the Earth, but not too close, because you don't want to have too many satellites. If you are close, of course, you need to have many satellites and the problem grows. You have to find an orbit which is suitable, gives you the least number of satellites, allowing positioning, good positioning, so that you must have, the requirement is to have at least 4 satellites in view at every time. De facto, you can have 7, 8, usually. You can count if you have the right app. And essentially this is it. And essentially this is it. The ground segment does a lot of work in this case, because the skills and most of the difficulties are on the ground, not in the space segment. Okay, here you see the distribution of the orbit of the constellation. They are on 6 orbital planes, separated in each orbit each other by 60 degrees. So there are 6 satellites on every orbital plane, and they are rotating with a period of 12 hours. Okay, so this is a broad description of navigation satellites. Let us, we spoke about technology demonstration mission. We will not say much about space station and human space flight in this course. Is a different, the difference is that in addition to all the system requirements that you may have, of course, the system must support life. And life supporting systems are a separate issue that are not part of this course. Simply, there is no time. There isn't any possibility to deal with this in this course. But we are trying to modify the laurea magistrale, the master course, so that in the second year there will be emphasis also on manned space flight. Let me say, and today the story, I mean, you are living in an interesting time because you have heard of the Artemis program. They should call it Artemis, but let us call, like the Americans use, the Artemis program, which is essentially a return to the moon. return to the moon with a much bigger infrastructure, with a space station much smaller than the orbiting space station around the Earth, ISS, which can host not permanently a small crew of astronauts. And so is a sort of pied-à-terre for travel to the moon. So it's quite interesting what is happening. But we will not treat manned space flight, or we will not treat life support systems in this course. Let me say before closing in these last 2 minutes a few words about defense satellites. Defense satellites fall into category: telecommunications, encrypted telecommunications, secure telecommunications, and most importantly, observation satellites. So are satellites which track, are so-called spy satellites. And if you think that spying is a bad thing, I hope in 2 minutes to convince you that spying is the best thing that you can do. The best thing, at least at military level. I'm not saying at other level, industrial spying is not a good thing, but at military level, yes. And the defense spy satellites had a crucial role in the maintenance of peace during the Cold War, for example, because satellites gave the possibility to each of the two superpowers to know what the other was doing, how many weapons, nuclear weapons they had, how many silos they had, because you can control everything from space. And imagine a situation in which you have two opponents who don't know how armed they are. You don't know if your opponent has just an arrow, a bow and an arrow, or he has machine guns and bazookas and so on and so forth. In this situation, not knowing what your opponent has, you have the tendency to arm yourself as much as possible to possibly counteract an inexistent enemy. Okay? So knowing what the other, your opponent has, allows you to keep the arm levels at the right level in order to counteract a possible attack. So defense satellites, which are Earth observation satellites with cameras and also sensors for detection of nuclear explosions, tests, and so on and so forth, played a crucial role in the maintenance of peace during the Cold War, and also today, Okay, so we close here for now, and we meet again tomorrow at 10 o'clock, same location, okay? Okay, I stop recording and goodbye to everyone.